Okay, good morning. So we're going to do a long talk about neutrons today. As you can see up here, we're going to talk about neutron construction, the Dirac and quark versions. Then we'll do electron capture of the proton, because you can turn a proton into a neutron, right? By electron capture, the reverse beta decay. And then we'll look at like my model and how it fits, and the neutron anomaly, which is this thing that neutrons, depending on how you measure the neutron decays at different rates. But first thing about that is it's very important to understand that it's not the decay rate. It's described as a decay rate, but if you look into it, a better term would be uh, like, I guess, decay rate. Yeah. But it's not individual. It's not how long a neutron takes to decay. It's the average time before a neutron decays. It's like the neutron half-life, the free neutron half-life is, I think, a better way of doing it, because there's a distribution. It's not like every single neutron decays at exactly that time. So there's because if it was decay rate, then it would be like everything does it at the same time, right? But if it's a wide distribution, then you can start to look at it. It's like, oh, wait, it's more like a half-life. It's, most of them will decay by this time, but some of them might last a bit longer. Okay, so these are important distinctions to make in experimental data. So just okay. So first, let's look at a proton. In my model, we've got space, gravity acts on space, any kind of variation in the quantum field. I'm going to use that term just for familiarity's sake for everyone. So there's a variation in the quantum field. If this is a density in the quantum field according to gravity, then this should just get exacerbated until and then you get a proton, because Casimir effect, the field lines are like tightened there and splayed out here, compressed in there. So protons are positive, the electron is negative. As the funnel around, basically, proton is sink into the hyperflow that is the surface of all event horizons. And on the antimatter universe, they're experiencing the same thing, only it would be because of the chirality inversion, and actually they're on that surface. It's sort of different, but charges would be reversed, chirality reversed, the complete inversion. Let's just think of heading towards an event horizon, because this is like empty space, and then empty space is flowing and getting more and more dense and more dense and more dense and more dense into more dense, and this is a sink. This is in my model. And then it gets absorbed into this. It gets basically like sucked into this, which is the evanescent flow. This is the surface of time. This is maxima. Everything's heading towards maxima. This is unity. This is like the surface of time. It looks very big, but actually it's very small. But because it's so compressed, it's so dense that it compensates. So there we go. That would be my model. Now let's look at a quark model of building a proton and a neutron. And I'm going to use my little trick to see, these are my pieces for building quarks. And this would be a up. Blue is positive. Play along. Up. Down. Okay, so we're going to build a, let's maybe go like this. Whoa. There we go. Okay. Impromptu stage change. So we're going to take one up and two downs. Oh wait, we're building a proton, right? Two ups. And one down. Okay, two ups and one down. Two positive fractional charges, two positive fractional charges, one negative fractional charge. These two cancel out, creating no charge. And even though I don't think it's included in the way that quantum mechanics makes it, I would say like, oh, well, that turns into the spin component because it's a positive and a negative. So if they were chasing each other, you'd get a neutral charge, which is the hole in space, surrounded by three axes of positive charge, which would be a proton, the proton-y part, like the positive charge. This is the positron, and this is the sort of the mass unit, because a photon chasing its own tail. So that's how we'd make a proton with this quirky method. Now, wait, if that is a proton, then what we need is to make a neutron. To make a neutron, you have to take an electron, which is three axes of negative charge, and push it into there to neutralize this, neutralize all of those three to make a neutron, which is sort of like the double cover. So that math doesn't really make sense to me in terms of the mathing. I mean, they neutralize each other, but there's three of these, and where do they go if the one proton made the first? Like, I'm sure they've worked it out because they had a lot of time to work out this mathy. Okay, but I'm just saying, what if we just think of it as that's three directions of flow, right? And that first pair that got neutralized, that's like that. Now, what you're doing is, and there's electron all around, right? This is a proton, so therefore it's surrounded by an electron. And when you make a neutron, you squish it in. But the way you construct a neutron according to quark mechanics is you take two downs and one up. Two downs and one up. Neutralized. Makes the first layer. Neutralized. Oops. Makes the double cover. Neutron. But I did that with 4 pieces one way, and it took me like 8 pieces. I know it's like they've worked it out with their charges, but it's just conceiving of it. So, and then Dirac neutron. Wait, let's go back up here. In a Dirac neutron, it is electron capture, and they describe it exactly like that, as if here's the proton, right? Here's the electron, because they are using sort of like, you know, this imaginary point particle that's going at c around, or something like c 101 1 over 137 c, orbiting around the core, right? And then what happens is very literally, and down in here, there's supposed to be there's a positive charge, right? And what happens is very literally, this gets pushed from the most inner hydrogen orbital to an interior, the same interior orbital as the charge component, creating the neutron, because you've enclosed the two flows. You've this complete thing, right? You have a sink, you have to have a flow to the sink. It usually takes up this much room, but you can compress it into a neutron as like sort of like the universal egg that has all the stuff built into it. And then when a neutron decays, what happens is, a neutron decays, what happens is one of the layers, basically, there you go, right? We neutralized two of these. There's one up, two downs, neutraled, made the double cover, extra big one. And then it breaks apart. So you lose a cover. So you still have a mass thing. And you have positive surrounding the mass. It's in there, so we can see. Wait, let's do that tilty thing. That was a good idea before. Positive charge. The neutron decays. You get a proton and the surrounding electron, which is effectively hydrogen gas. Plus, a neutrino gets spun off, which I think of as the spin component. Like this all used to be compressed and spinning, but instead of the energy being rotational, it becomes radial. And so the neutrino is the spinny part. Basically, that spin flung off as a spin without flowing in or out of the membrane of time itself, sort of thing. Now, this thing about the neutron anomaly comes from the fact that depending on how you measure the neutrons, sometimes they decay faster or slower. And there's not really a thought about that because there's no connection between gravity or other things, especially, and the neutron. There's not really, the neutron is supposed to be having no interactions with things. It's neutral. It doesn't do interactions because it has no charge component, but in my model, it's because it is the double cover. And when it decays, it will become hydrogen. So this does have a spin component. And when do you get neutrons? When do you get hydrogen being turned into neutrons? Oops. Part 2, because I'm a goof. When do you get neutrons, hydrogen turning into neutrons? When do you get hydrogen turning into neutrons? There's two instances. Either it happens in an atomic nucleus, where it's reverse beta decay, as it's called, and this happens, the electron gets reabsorbed into an interior, like an interior orbit, and now it's a little hermetic nugget. Or, so that's a very dense, let's just imagine, like the atomic nucleus is the densest thing. It's like a neutron star. This is as dense as things get, basically. It's on the border of being even chartable because it is so dense. Gluons and all of this is basically at the total limits of our math is about to break down. We'll do some renormalization here and there, maybe to try and make it make sense. But really, this is where our fabric of space-time is folding in on itself, and we're not sure what to do. This is where we are, because it's the nucleus. I mean, this is as dense as you get. And where's the only other place that you're going to find this happening is at a neutron star, which is, so gravitationally dense. The metric is that dense that it basically gets pushed in. There's not enough room. The gravity is so dense, it's just like no gravity, because gravity is not just downwards. Gravity is a funnel. Okay, you can be this big at this gravity. When you're at a very high gravity, you don't get to be big. You only get to be a neutron. Only at the very skin of the neutron star is there going to be protons released, because we can see them, so therefore there must be protons, because there's photon interactions and stuff. But it's basically only neutrons. Why? Because very high metric, like the nucleus. So my proposition, or my suggestion regarding this whole neutron anomaly, is that the methodology is the ish. What we can do is figure out which of these methods gives the longer lifetime, and then like double, quadruple, go like whatever you can do, maximize the field densities of every single thing that's happening in their lifetime, and then measure the lifetime and see if it changes. Because in a unified model where space-time and gravity and charges, they're all interlinked as a single thing. Charges made from the flow of space. Gravity is the metric of the space that causes you to fall down, basically the metric. Right? And energy impinges on the metric, but the metric also gives, because it's kind of like the wave equation. And that's why gravity, it's a spontaneous self-excitation towards maximal density of the universe. But regarding this, if we just go cray with the field densities, we can find out if we can manipulate the lifetime of neutrons. And then maybe we can make neutrons live forever. I don't think we can make them decay faster, but maybe. We'll find out. But this is my suggestion. We need to do a version of the bottle method where everything is like 10 times, all the fields are 10 times as strong. Just redesign it a little bit so that it's like that. And same with the beam method. Make everything like just extreme to see what's affecting it or not. So we can really get a handle on this, because in an integrated system, it is all one material, space-time. And the tension, or you could even think of it, if you don't want to believe in a flow, then you can just say that the metric tensor, like as there's gravity, we don't see it because there's matter distributing it and doing a whole messing with it. But at the quantum level, the metric tensor on singular space-time is creating charge by this bunching up of charge here, creating positive, and divergence of charge or space-time from the metric tensor, basically like a pole, however you want to think about it, but basically it's an unevenness. And because of that unevenness, charge manifests from that, because space is a perfect dielectric. Charge won't go past one quark away from, not one quark, one like Planck length away from where it is, unless it's got something to bounce against. Okay, and in free space, it'll just like shoot off as far as it can, but all it's looking for is reconnection. Anyways, that's a really long video. Peace out. I gotta get to work.